In this example, we're going to hope to use a trig identity to help us simplify what's in that integrand. For this particular problem, we're looking at the integral of sine cubed of x times cosine squared of x. And now for us, what's important in this example is looking at what the sine is on the power is on the sine as well as the power on the cosine. And what we notice from the sine term is that that sine is raised to an odd power. The reason I want to point this out explicitly, it's because of this odd power that we'll know what type of substitution or trig identity is going to help us out here. Because of this odd power, we're going to try and build towards a u-sub. And we'll go through the reasons why this will help in a few moments. So with these types of problems, we're going to be able to substitute Pythagorean identities to help us out. That's where we're headed. But what I want to do first is just take the original integral and just take away one of those sine terms, or factor out one sine term to leave us with a sine squared of x, still with that cosine squared of x, but take that one sine term that we factored out and just put it at the end of the integral. So again, we just factored out one of those sines, and what we see now is we have a sine to an even power, as well as we still have that cosine to an even power as well. The reason why that's important for us is this is going to help us build towards a u-substitution. Because whenever we have only even powers of sines or only even powers of cosines, as we'll see in a moment, we're always able to shift those into the other trig function through a Pythagorean identity. So in this case, the u-sub that we're going to build towards is a u-sub with u equals cosine, just because we're going to want to try and cancel out that lonely sine of x at the end of the integral. All right, so let me just show you these identities that we're going to be working with. So the Pythagorean identities, there's 3 of them. And basically, we're just going to match the identity with the trig functions that we have in that integral. So the last 2 really are out for us because we're not working with tangents or secants. We're not working with cotangents or cosecants here. So I'm just going to get rid of those right now. And if we look at this other one, we can write either sine squared in terms of cosine squared stuff, or vice versa in this case. What we're going to want to do here, because we have this sine sitting at the end of the integral, is we're going to try and turn everything else into a cosine term. So our goal here will be turning that sine into a cosine. So that's where we're heading next. And the way in which we can do that, we can take this identity and just solve for, well, sine squared. So sine squared of theta are always equal to 1 minus cosine squared of thetas as well. And this is going to be what we substitute into that sine squared in that integral. So let's go ahead and do that next. So we have 1 minus cosine squared being substituted into our integral for what was previously that sine term. We still have that same cosine squared. Oops, I need a cosine of x, not a cosine of theta. We have that same cosine squared term that was originally there in our integral. And next, I'm just going to put that sine of x term that we left at the end of the integral that we're going to cancel out with a u-substitution in a moment. So the point that I want to make before we go ahead with that u-substitution is that we have everything in this integral is in terms of cosine stuff, except for this last term, which is only the sine term. And that's the only sine of x in this integral still. So if we do a u-substitution here with u equals cosine, the derivative of cosine is a minus sine. Now solving for dx in terms of du, what we'll get is a du all over that minus sine of x is equal to dx. So we can substitute both of those aspects into this integral. Everywhere there's a cosine, replace with a u, and we can replace that dx with du over minus sine of x. So let's go ahead and do that substitution now. So we have this first term that becomes a 1 minus u squared, because that cosine squared just becomes a u squared now by our substitution. That cosine squared term, that thing just becomes a u squared. We still have that same sine of x sitting there at the end. And now the dx for du term, that becomes a du all over minus sine of x. And lo and behold, we see that those sine of x's cancel out. So we've built our u substitution successfully. And the remaining terms in this integral, I'm going to pull that minus sign, just put it out in front. So we have the integral of minus, and then we can distribute this u squared into both terms in parentheses. So we get a u squared minus u to the 4th power du inside of that integral. And now what we have is a variable raised to a power, so we can use the antiderivative power rule. So we have this is equal to minus the quantity 1 over 3 u cubed minus 1 over 5 u to the 5th power. And then, of course, our plus c. And the last step for us now is to just put in what was originally called u. And again, that's going back to our substitution from before. Everywhere there's a u, we replace that with cosine. So the final antiderivative in this problem is 1/3 a cosine cubed of x minus 1/5 a cosine to the 5th power of x. And then plus c. So we're able to, given this integral, where at least one of the terms, either the sine or the cosine, had an odd power, we're able to factor one of those things off. In this case, it was the sine that we put at the end of the integral, and then we built towards a u substitution to cancel that single sine of x through the substitution itself. So our final answer down below.